Okay, guys, welcome. In this video, we're going to talk about a formula for the Fibonacci numbers. Now, I want to come out and just say what they are, what the formula is first, and then we'll go about seeing maybe how you would come up with something like this. Okay, but the formula for the nth Fibonacci number is given by 1 over the square root of 5, and then times the difference of these two expressions here, right? So we have 1 plus square root of 5 over 2 to the n minus 1 minus square root of 5 over 2 to the n. Okay, now for when n is equal to 0, this is trivial because you get 0 is equal to 0, right? Because this would become f0, right, which is 0, and these would become 1 minus 1, which is also 0. Now for the inductive step, we'll assume that this is true for all k that are less than or equal to, and it should not be equal, right? So strictly less than n. Right, and of course we want to show this is true for f sub n. Well, f sub n is, of course, we know that it's made up of the two previous Fibonacci numbers, right? So we can write out what these would be. And of course, the only thing that's going to differ between these is these two powers. Now, if we combine like terms, right? If we combine, sort of have like this reddish purplish color here. If I look at these two terms here, I can factor out the 1 plus square root of 5 over 2 to the n minus 2. And then what I'll have left over is still 1 left and then plus 1. And then a similar trick for the orange part, which is the minus square root of 5 terms. Now, if I combine like terms and I simplify the inside of both of these parentheses, I'm going to get a 1 over square root of 5 out front. And then I get this 1 plus square root of 5 over 2, 1 minus square root of 5 over 2, both to the n minus 2 power, and then they're each being multiplied by these expressions. So now if we can prove that 3 plus or minus square root of 5 over 2 is 1 plus or minus square root of 5 over 2 squared, then we have it, because then we'll have that both of these are now to the n power, right? And in fact, if we square 1 plus or minus square root of 5 over 2, you'll find that once you square the top, again, the only thing that's different here is the plus or minus of both of these, but they both carry over the same way. We'll get a 6 plus or minus square root of 2 over 5 all over 4. And then, of course, you can divide the top and bottom by 2, and you will get that you have 3 plus or minus square root of 5 over 2, right? So then that proves that this term right here is just this expression squared, so then we get to the n power, and the same holds for this side. All right, so it's not too hard to prove that that's the formula. Now, to see where this formula comes from, let's pretend that we didn't know that formula. All right, and we're going to look at the ratios of the consecutive Fibonacci numbers to see how fast they grow, to see if that suggests itself to some kind of growth rate. Now, if you look at consecutive Fibonacci numbers, right, so you have 1 over 1, which is 1, and you have 2 over 1, which is 2, and so on and so forth. And it looks like if we do this for long enough, it's starting to settle in at around 1.618, right? So that gives us an idea that this might be a geometric progression, right? So we might have some kind of geometric or exponential function going on here. So we're going to assume that g sub n is c times q to the n, right? So we're going to let g sub n be a possible formula for the Fibonacci numbers. Right, and it's just some exponential, some arbitrary exponential equation here where we have some constant c times q to the n. All right, and we also want this to satisfy that g sub n plus 1 is equal to g sub n plus g sub n minus 1. Okay, well, if this is true, and we define g sub n to be c times q to the n, then plugging this in will give us c times q to the n plus 1 equals c times q to the n plus c times q to the n minus 1, which we can simplify through if we divide everything by c times q to the n minus 1. then we get q squared is equal to q plus 1. And then, of course, we can, since we have a quadratic, move everything to one side and try and solve this. And then we find that q is equal to 1 plus or minus square root of 5 over 2. Right? And if you type these into a calculator, you'll get that this is about 1.618034. And if you do the minus square root of 5, you get negative 0.618034. Right? So this gives you two possibilities for your g sub n here, right? You could either get g sub n be 1 plus square root of 5 over 2 to the n power, or we'll call gn star 1 minus square root of 5 over 2 to the n power. And of course, both are multiplied by c. Now, neither of these together would give you c, right? Give you the Fibonacci numbers, right? Because, for example, if n is 1, you get this crazy 1.618 or negative 0.618 number, right? So we know that neither of these give us the exact Fibonacci formula. But however, we do know that if we take g sub n plus 1 minus g sub n star, right, we can plug in their recurrence relations here and rearrange to get g sub n minus gn sub n star plus g sub n minus 1 minus g sub n minus 1 star. Now, if we look at g minus g star for any n, we'll find that the first one works out well because we get 0. And if we look at for n equal 1, we get c times square root of 5, right? Now, if c is 1 over square root of 5, then we have it, right? Because then we get the first Fibonacci number, right? So now we can get the nth Fibonacci number by taking g sub n minus g sub n star and dividing it by square root of 5, right? So that gn star, now one thing that you'll notice here is since this inside of this term here, this base of our exponent here, since that's a negative number, that's going to go to 0 fairly quickly, right? And of course, it will go to 0 definitely as n goes to infinity. So that means that g sub n gets close to your f sub n, your nth Fibonacci number, as n goes to infinity. Okay? And of course, g sub n, this base, this 1 plus square root of 5 over 2, is a famous number known as the golden ratio. Right? And if you end up taking a number theory course, you'll probably spend a good amount of time talking about the golden ratio. All right? But that concludes the proof for the Fibonacci numbers here. So I hope you enjoyed, and I will see you next time.